Let's now recap what we've learned so far about capacitors so that we can have everything in mind that we need as we build on this background and move the discussion forward yet again. So you recall we defined our capacitor as a circuit element, which is made out of these particular material components. I've got two metal plates, each with an area A, separated by a separation D. The way this system interacts with the outside world, what defines its terminal characteristics, are the amount of charge Q that has flowed in along this top wire, with the corresponding minus Q having flowed in from the bottom wire, or equivalently a plus Q having flowed out from the bottom. So there's Q is one of the terminal characteristics, the net charge that's flowed in here. The other terminal characteristic is the voltage between the minus lead and the positive lead. There's a characteristic equation then relating these two external quantities where they turn out to be in direct proportion to one another. The amount of charge you can store on this thing, its capacity for charge storage, is proportional to the voltage which you apply times the proportionality constant C, known as the capacitance. And we had a particular formula for it in the parallel capacitor case, the parallel plate case, epsilon naught times the area of the plates divided by D, their separation. We then use this information in our arguments about total potential energy in order to infer that the total energy stored, the potential energy stored in this kind of a physical arrangement, should equal 1/2 the charge stored on the system times the voltage of the system. Technically, this of course would be the voltage going from the minus lead to the plus lead. By using our above characteristic equation, we can write this as in fact either 1/2 CV squared. Now we don't have to worry about the direction of the arrow, so I haven't written it because it's V squared. If we have the minus sign on V, it's not going to affect the final result. And another form we have for it is by substituting in a different way, the square of the charge divided by twice the capacitance. So we actually have three equivalent forms for the potential energy in this arrangement of charges. The next thing that we did was to confirm conservation of energy. What we decided to do is to see how much work it would take for us to actually create a charge situation on our capacitor. We did this by computing the total work that we would do if we would, by one tiny amount of charge at a time, plus dq, move positive charges off of the bottom plate and move them up to the top plate. That then led us to an integral which we carried out, and very nicely we found that in fact indeed the work it would take to charge up this capacitor all shows up entirely here as potential energy.